Hello everybody and welcome back to part 2 in a series of videos where I go over the entire build process and design process of my next model rocket, Velox E. If you haven't seen the previous video, I recommend you do so because I kind of went over most of the overall design of the whole rocket and a bit of the algorithm as well, which I'm going to kind of skip over in this video because there's a lot of other things I want to talk about, so I'm only going to briefly go over it again. So as I just mentioned, the headline of this new rocket is the fact that it has electronics on board that will be able to read IMU data, so acceleration and gyroscope data, to be able to detect what part of flight is it in, so like liftoff, burnout, apogee, touchdown, all that sort of stuff. And it'll be able to rotate a servo motor to deploy the parachute when it's at apogee, and it'll use all that data to figure out when to do so. In the next video I'll go over the parachute deployment system in more detail, but all you really gotta know for this is that it involves a servo motor rotating to deploy the parachute. This, by far, was the most complex part of this whole process. It's the first thing I worked on, was the programming and everything, and I'm still really working on it as of recording this video. It's mostly done, just a couple things need to be tweaked out, but it's working as far as I can tell. So with that said and done, let's just go over the hardware of this whole system first. The whole system is comprised of 3 main components: the Arduino Nano 33BLE microcontroller, 3-volt Adafruit microSD breakout board, and the SG90 servo motor. These are all connected together with jumper wires and all that sort of stuff, which I'll get to later on. First off, let's start with the microcontroller, the Arduino Nano 33BLE. So this is kind of like the brains of the whole operation. Everything is connected to this thing, and it kind of handles all the data. It operates on 3.3 volts of power, and it houses this thing called an IMU, which I've mentioned before but haven't really explained what it is. An IMU is basically a little computer thing that has 3 different, I don't know what you would call them, sort of measurement things inside of it. Number 1 is the accelerometer, which obviously measures acceleration in all 3 axes, so X, Y, and Z. Yeah. It also has a gyroscope, which measures kind of the tilt of the rocket, which I mentioned in the last video a bit as well, just how much it tilts in degrees and stuff like that in all 3 axes. And it also has something called a magnemometer, which is not really useful for this because I'm pretty sure it's just used for like cardinal direction and things like that, which we don't really need for this specifically. The main 2 things we're going to be using for this is the accelerometer and the gyroscope, the accelerometer especially. It's going to be the main thing to use when we're trying to tell the rocket what stage of flight it's at, because obviously when it's lifting off it's going to have a lot of acceleration, and when the rocket depletes its fuel, for example, it's going to be slowing down, so it's going to have a lot of deceleration. This is also where the power from the batteries is going to be connected to, which I'll get to towards the end of this video, how everything is powered up. I do want to make a quick disclaimer, however. If you are planning to do a similar project like this that's going to use the acceleration and everything to measure the height of the rocket, how high it goes, and when to deploy the parachute and stuff like that, I would definitely recommend getting a slightly different board to this. Instead of the 33BLE, I get the 33BLE Sense, which is a slightly different version, just has the word Sense at the end. And that actually comes installed with everything that this has, but also a barometer. And a barometer measures the pressure in the atmosphere around us to figure out like how high the thing is, and that would be a lot more effective and a lot less complicated to figure out when the rocket is at apogee, because you could just tell the computer when it starts falling back down to the ground, deploy the parachute instead of doing all this acceleration type business. And when I was planning for this project before, I kind of just didn't know that this one existed. This should still work in theory. Next up is the Adafruit breakout board for a microSD. This is going to be where all of the acceleration data and everything is going to be stored into an SD card, because another goal of this project is that I can retrieve all the flight data after the flight and put it into a graph or something to see, you know, how fast the rocket went and all that sort of stuff. I want to be able to see the exact flight profile. Now this is also going to be useful in case the rocket fails in some way. We can, you know, where did it fail? Was there some sort of glitch in the programming? We'll be able to see from the flight data, hopefully. While I was actually developing this whole system, there was another microSD breakout board that I was using, but I could never get it to work. It's one that I saw a lot of other people were using. It never really worked for me, and it took me a while to figure out why. Basically, that specific breakout board uses 5 volts of power. The Arduino Nano 33 BLE, the one I'm using, only outputs about 3.3 volts of power, so there wasn't enough actually getting to the board. In theory, it should have been fine because there's a voltage step down thing inside that little computer board, and it just takes 5 volts and brings it down to 3 volts so that the SD cards can work properly, because SD cards only use 3 volts. So it should have been fine with my 3.3 volts going into it, but I think that step down thing, the unnecessary extra process, was just not giving enough power to the SD card. So I bought the one I'm using now, which doesn't have any regulator on it at all, and it just feeds indirectly into the SD card, and now it works fine. The final piece of this puzzle is the servo motor. It's pretty simple. It's just a bunch of gears rotating this arm around, and it's connected to the Arduino board. It operates off 5 volts of power. It's very light and small, which makes it pretty good for this. It's not the strongest servo motor. You can get bigger ones that are a lot stronger, but hopefully, you know, it'd still be able to rotate under the pressure of the parachute. All 3 of these components are then going to be connected using a breadboard, which is not a physical, literal breadboard used to chop things up. It's a board basically with a bunch of holes in it. It allows you to connect a bunch of microcontrollers and all these different things without actually soldering them together, because that's a permanent thing. This is like, you can just easily connect and disconnect a bunch of different things in a bunch of different patterns that you want. Everything's connected together using these things called jumper wires, which are just wires with these little prongs at both ends. You can either get male or female connectors. All the boards, like the Arduino and the breakout board, have these things called headers, which are just metal kind of prongs that are inserted into the breadboard, and that allows you to actually connect the boards to the breadboard and also connect all the jumper wires to them. And all of these things are connected to the various ports of each of the boards. I'll put a schematic in the description and also hopefully right there. You probably can't see it very well, but that's all the wires and all the connections and everything. I'll post all the documents and everything like that of all the different components in the description so you can read about them yourselves if you're, you know, planning to do something like this yourselves. So that is basically all the hardware aspect of this entire system. Now we're going to get into the kind of nitty-gritty complex bit about the programming for this whole thing, because that's how this whole thing works, is programming. I'll post the raw code in the description as well, so you can copy and paste it or whatever if you're going to do something like this. It's obviously going to need some tweaks depending on what components you're using, but this code should work for most Arduino boards and other components that are commonly used with it, so just keep that in mind. Now, I've had very little programming or coding experience before this, and literally no programming in this language, which is C, I think, before this, so this is by no means the best code or the best efficiency, and I had to get a lot of help, but it's working, so we're just gonna go with it. So at the top here are the libraries. Now, if you are going to use this code yourself, these 2 lines are something you will probably have to change yourself. These are just the pins that you have connected the servo and the SD card module to in your Arduino. I've got my servo connected to pin 9, and I've got my SD card connected to pin 10. You're probably gonna have to change this depending on which ones you connect it to. Over here then are your flight states. So these are the critical parts. You've got your waiting, your idle. The waiting is basically just a way for program to be like, if something fails, you go back into the waiting stage, you're not ready to fly. The idle stage then is when everything is up and running, it's ready to go, it's waiting for liftoff, and obviously liftoff, burnout, apogee, and touchdown. And yeah, the flight state at the start is set to waiting. Here then is just a bunch of variables for the LED flashing. I have the LED flashing blue when it's in idle, so I know on the day I can just look at the LED on the card and be able to see, is it ready to go, is it flashing? And it flashes every 500 milliseconds. Here is just a way to prevent anything repeating itself, so I've got a servo rotated equals false. That means to prevent the servo motor from rotating multiple times, so if it rotates once, the servo rotate is equal to true. No other commands can be sent to rotate the servo afterwards, so it only rotates once during the flight. Here are just other variables to keep track of flight time, so yeah, flight time is equal to 0 at the start, obviously. Same with liftoff time. And this line here is very important, this one here, the auto threshold. In a program like this, it is very important, especially if it's taking control of a very flight critical component, which is the parachute deployment. Everything relies on that servo motor rotating at least at some point. And we need to make sure we have a redundant backup thing to make sure that happens. So this basically is a way of saying after 6.5 seconds, this is in milliseconds, 6.5 seconds, the servo motor will automatically rotate if it hasn't already. And I got 6.5 seconds because that's roughly how long it took for Falcon Bobby 2.0 to reach apogee. And since this is going to be a very similar rocket in terms of mass and all that, I will probably change this as I actually build the rocket and get more accurate mass and stuff like that. Over here then, we're just defining the acceleration and gyroscope in all 3 axes, X, Y, and Z. Here we have a few functions over here. We have this LED function, so that sets to blue. Then we have a function for the rotate servo. We say rotate the servo for 1 second and then stop the servo from rotating. 90 is the idle stage. Over here then in the void setup, this is the very first thing that kind of happens and moves in the program. We set the LED to blue over here, and then we also do this kind of cool thing where the servo very slightly rotates at the very start to make sure, yes, the servo motor is working. It is, you know, ready to go. Rotate for 0.1 of a second, 100 milliseconds, stop, then another millisecond, go again, another milliseconds, and then stop. This is what it would look like running. Now, in this void begin area, this is completely temporary. It's literally just while I'm testing it on a laptop, I can say the program will only start once I type S into the program. Then it will actually start. But on the day, I want this all to happen automatically as soon as I turn on the computer, so this whole chunk of code here is just going to be gotten rid of. In the flight, it will just go straight to this void loop function, and the rest of the code is in this void loop function because the loop makes it happen over and over and over again. So here, if we're in the idle state, which will happen automatically if everything checks out, the LED will begin flashing, and we initialize a bunch of the stuff. So we initialize the IMU, we initialize the SD card, and if it fails at any point, we go back into the waiting stage because I won't be able to check if it's working. The only thing I'll be able to see is whether the LED is flashing or not, and the LED won't flash if we're in the waiting stage. So if it fails, it goes back into that waiting state. But if everything's fine, it just continues. We begin the data logging, so we open the file in the SD card, make sure all that is working, and again, if it doesn't, we go back into the waiting stage. And we have this while loop here, so we say while we are not in the waiting stage, so if we're in the idle, liftoff, burnout, apogee, anything else during the flight, all of this code starts working. This is also more code to tell the computer about the auto-rotating after 6.5 seconds. So if the servo hasn't rotated already, and we are not in the idle stage, so it's only after liftoff that we start counting for 6.5 seconds. If the flight time is more than or equal to the auto threshold, which is 6.5 seconds, then we rotate the servo automatically. And we set servo rotated equals to true, so that the servo motor does not rotate more times. We also begin the data logging, so all this data here is then put into the SD card and also displayed on screen. All this stuff here is to just also calculate the total acceleration in G's, and this extra bit of code here is just a way to measure the total displacement in gyroscope tilt instead of the rate of tilt, because by default the computer, the IMU, measures the rate of gyroscope displacement, so how fast it rotates, instead of total amount of rotation it does. So we can't just say if it rotates by 90 degrees, rotate the servo. That does not work. But thankfully with this, we are able to, we're able to do that now. So now we get into actually detecting the different states of flight. So first, to detect liftoff, we have to say if it's in the idle state, and if the total acceleration is more than or equal to 1.75. We don't want it to be too sensitive, but we also want to make sure it actually detects it. So 1.75 G's of acceleration, that means the rocket has lifted off, and the state is then changed into the liftoff state. To detect burnout, then we have to make sure is the state in liftoff and the total acceleration is less than or equal to 0.45. Because as the rocket depletes its fuel, it's going to be decelerating instead of accelerating. And keep in mind, like, just 1 is the kind of idle stage, like when you're sat still, not doing anything. So if you're less than 1 times the force of gravity, you're going to be slowing down. And the gyroscope displacement and everything is reset to 0 just to make sure there isn't any, like, false glitches or anything making it seem like the rocket is tilted too far in one direction. To detect apogee, then, we have, and again, redundancy is very important, so we have 2 ways, actually, of detecting apogee. We're going to say, if it's in the burnout stage, and the servo has not already rotated, and the total acceleration is more than 0.95, so if it's very close to 1, roughly, so aka still, or if we rotate more than 65 degrees in the Z or Y axis, then we also rotate, because if you can imagine, when the rocket begins falling back down to the ground, it's going to be turning to go nose down into the ground. So these are just two ways of being able to detect apogee, and just more redundancy. Also, we say if we're in apogee and the servo is not already rotated, we rotate the servo, and we turn servo rotated to true, so it doesn't repeat. Finally, then we say detect touchdown if we're in apogee and the total acceleration is more than 1.5, so when it hits the ground, you're going to experience a bit of an acceleration or deceleration. Then we're in touchdown, and if we're in touchdown, the LED stops flashing, we wait 10 seconds, and then the program shuts off. The last bit of code here then is just the flashing LED codes, and that's it. That is all 259 lines of code for this program. That was a lot, I assume. Finally, we are going to talk about how everything is powered, because until now I've only just been connecting this whole system to my laptop via USB, and that's how it's getting all its power, and that's how I can write all the code to it and everything. But when it's in the rocket and it's going to go in the air, I can't physically connect it to a cable to my laptop unless I get a really long cable. It's going to have to be completely internal and work on its own power. So the obvious solution is a battery. But the type of battery I'm going to use is very important. I've seen a lot of people use like a 3.7 volt, I think, lithium ion battery, I think that's what it's called. It's very light and it has a long battery life, but it doesn't actually draw enough power. There's not enough volts going to the system to operate everything, because the Arduino board uses 3.3 volts. The breakout SD card reader thing has also 3 volts, that's 6 volts. And the servo motor uses 3 to 5 volts, so that's 9 volts roughly. So instead of using that 3.7 volt lithium ion battery, I'm going to be using a 9 volt battery. This is a better solution because it outputs 9 volts, obviously, hopefully enough power to operate everything at the same time. There's two main disadvantages to this battery, however. The first is that its battery life is a lot shorter than the lithium ion one, but that's not too bad because the whole system is only going to be running for a couple minutes at a time. I mean, I plan to turn the computer on like maybe a minute before we launch, and then the rocket is only in the air for like 20 seconds max, and then it's going to automatically shut off once it touches the ground. So the battery life isn't really much of a concern. It's mainly just testing and stuff beforehand. I want to use the least amount of battery consumption. And also this battery is quite heavy, which is obviously bad because you want to make your rocket as light as possible, but also good because of some center of gravity and center of pressure balances and stuff like that. I'll get into that in the next video. But being able to have something kind of heavy to put in certain areas of your rocket can really help stabilize it a lot better. As I said already, I'll get into that in a future video. So for the 9 volt battery, I just bought a battery case with some wires coming out of it. Now those wires that came with the battery case had two big problems. The first is that they were too short, and second, the core of the wire is frayed, which basically means it's not one solid wire, it's a bunch of tiny ones put together, and trying to insert that into the breadboard is very annoying, very tricky, and it's a very poor connection as well. So I bought some different wires that had a solid core in the middle, so it's a lot more sturdy and much easier to connect into the breadboard. I connected the two wires up by soldering them together. It's the first time I ever soldered, by the way, so it's not the prettiest. And also shrink wrapped the connection to make sure it was very sturdy. And all the connections, in fact, for this entire system need to be very sturdy because the rocket is going to be under a very high vibration environment, and that's going to be very easy to disconnect some wires mid-flight, and that's going to be very, very bad because one of those wires disconnecting is going to screw up the whole thing. Another thing I added was a switch. It was just a very basic on and off switch connected to the positive wire of the battery connector so that I could easily just flick it on and off during the day of flight, and I don't have to worry about manually connecting up wires and stuff like that. When I first plugged the whole thing in for the first time after soldering, I was very pleased that it actually turned on because there's a lot of factors that could have gone wrong, like not enough power or something, or one of like my soldering job is just terrible. Thankfully though, it seems everything is working and the servo motor rotates as well as all the other operations happening in the system. And with the whole system powered up and ready to go, that is basically the end for this whole computer system shenanigans. This is by far the most complicated part of this whole rocket, and I'm really happy that I managed to get it working on the ground at least. That's not to say that it'll work in the air, that's a completely different thing, but in theory it should, and we'll only know until we actually fly it. The next video, as I mentioned, is going to be on the building process of the rocket and a lot of the 3D printing components and assembling and all that sort of stuff. So make sure you stay tuned for that. And if you're also wondering still what this whole rocket is about, make sure you watch my previous video because it goes into the overall design. Anyway, thank you for watching and I will see you in the next video. Goodbye.